Algebra 2, let's move into lesson 16. In lesson 15, we talked about what is a trigonometric identity. Today, we're going to prove trigonometric identities. First of all, to get our brains warmed up, which of these statements is a trigonometric identity? Provide evidence to support your claim. If we look at statement 1, I'm having pen issues this morning. Statement 1. We see that this is just a reordering of the Pythagorean theorem that we talked about a few lessons ago. Sine squared theta plus cosine squared theta equals 1. If you just subtract cosine squared theta from both sides, you get statement 1. So the Pythagorean identity is true for all real numbers. Therefore, statement 1, this is my therefore, is an identity. So let's look at statement 2. The functions on either side of the equal sign are identical, so they're equivalent. So the graphs on either side of the equal sign are the same, therefore they are an identity. Oops. If I look at number 3, we have this and that. The graphs of the functions on either side of the equal sign in statement 3 intersect. The functions are not equivalent. If you threw them in your graphing calculator really quick, you would get a graph. Let's see. The first one would look something like this. This would be 1 minus cosine theta, and then 1 plus cosine theta would be opposite, 1 plus cosine theta. So, not an identity. So statements 1 and 2 are, but statement 3 is not. Okay, using statements 1 and 2, create a third identity statement, statement 4, whose left side is sine squared theta over 1 minus cosine squared theta. If you look, I have statement 1, sine squared theta equals 1 minus cosine squared theta. And if I'm just going to divide by statement 2, that'll give me 1 minus cosine theta over 1 minus cosine theta. Now I'll show you really quick. Here I have the difference of two squares. 1 plus cosine theta, 1 minus cosine theta. This is going to be some of the tricks you're going to have to use to prove these identities. So I can factor the numerator, and then I can simplify. So what I really get here is sine squared theta over 1 minus cosine theta equals 1 plus cosine theta. Okay, and this is actually valid. Goodness, I miss my pen. It's valid for all theta, where both sides are defined. I mean, obviously, well, in the denominator here, that cosine theta could give us problems, but we have a whole number in there too, so that'll never be 0 on the bottom. It could be negative, but it's not 0. So, for which values of theta is this statement valid? If I look at just the left side, so cosine theta, we're always worried about the denominator being 0, But if we get a value of theta, which gives us cosine equals 1, then the denominator will be 0, because 1 minus 1 is 0. So that will definitely give us problems. And cosine theta equals 1 happens at happens when theta is 2 pi, or factors of 2 pi. Okay, the right side, you're good for all values of theta. Okay, so the equation's true whenever both sides are defined, which is for theta that is not a multiple of 2 pi. Okay, this is where you're going to have issues. So theta can't equal any factor of 2 pi. Okay, discuss in pairs. Well, we're going to discuss here together what it might mean to prove an identity. What might it take to prove, for example, that the following statement is an identity? Here we provide an explanation. Back up a little bit though. What does it take to prove an identity? Well, you sort of need to know that these are in fact equal, and then we can always talk about the domain. Okay, they have to be equal for the same domain. But making sure these two sides are equal and have the same domain isn't quite enough, and that's why we're practicing this. It's not quite enough work to make sure it's an identity. So to prove an identity, you have to use logical steps to show that one side of the equation and that identity can be transformed into the other side of the equation using already established identities such as the Pythagorean identity or the properties of operations. We're going back into Algebra 1. Actually, we're going into like pre-algebra, 6th grade math, talking about operations. It is not correct to start with what you want to prove and work on both sides of the equation at the same time, as the following exercises show. So what the following exercises are going to show is we're going to have a left side of the equation and a right side of the equation, and you just work and work and work to prove that they're equal. Well, you can't do that, and that's what we're going to show. What you actually have to do is take one side of the equation, do a bunch of steps, do a bunch of steps and prove that it equals the other side of the equation. In this exercise, you'll see how if we try to solve both the left and the right side of a possible identity at the same time, how it doesn't work. So first of all, let's look at this example. It says use a calculator to graph the functions f of x equals sine x plus cosine x and g of x equals square root of that mess. To determine whether the left side equals the right side for all theta for which both functions are defined as a valid identity. Okay, both functions are defined as a valid identity. You should see from the graphs that the functions are not equivalent. So first I graphed sine x plus cosine x, and I got, let's do this different. Okay, this is the first graph. Okay, then I graphed negative square root of 1 plus sine x cosine x. And I got this fun shape. Okay, that right there shows me that they're not equivalent. So just looking at the graphs, you can see that the functions are not the same. They would overlay each other perfectly if they were equivalent. Again, the purpose here is to show you if you start with the goal of a proof, you can end up proving that a statement is false. Okay? So here we're going to see how a line of reasoning can go wrong, how your thought process could lead you astray. All right? So suppose that Charles did not think to graph the equations to see if the given statement was a valid identity. So he set about proving the identity using algebra and a previous identity. His argument is shown below. First, we have the equation for theta is any real number. Using the multiplication property of equality, he squared both sides, which gives, here we use FOIL, first, outer, inner, last, and we got this part right here. And here, if we square this side, the negative becomes a positive and the root cancels out. So I have 1 plus 2 sine theta cosine theta. Using the subtraction property of equality, subtract from each side. So we're subtracting those away, which leaves us with sine squared plus cosine squared on the left and 1 on the right. Okay, this right here is the Pythagorean theorem, the Pythagorean identity. So you can replace this by 1 to get 1 equals 1, which is true. Therefore, the original statement must be true. And that's where you come into problems. Okay, our graph tells us it's not true. The algebra we used tells us it's true, but you cannot start with the original proof to make sure that it is a identity. Okay, you're using something to prove itself, and that doesn't work. Okay, so let's look at walk through some different ways to approach proving the identity we've talked about at the beginning. Proofs make use of some of the following properties of equality and real numbers. So these are all of the properties we've learned through your math career so far. Some of them you don't even know you know, some of them you remember learning, etc. We've learned them in geometry, algebra, reflexive, symmetric, if A equals B, then B equals A. Transitive, if A equals B, B equals C, then A equals C. Addition, if you add something to both sides, you're good. Subtraction, subtract it from both sides. Multiplication, I can multiply something both sides of the equal sign. Division, I can divide something from both sides of the equal sign. Substitution, associative properties, I can regroup. Commutative properties, I can add and multiply in different orders. And distributive property. Okay, this works multiplying something through parentheses or factoring something out. Okay, this one I've used a lot doing your lesson and your problem set. So fill in the missing parts of the proof outlined in the tables below, then write a proof of the resulting identity. We're going to start with Pythagorean identity. When we divide both sides by the same expression, we introduce potential division by 0 when cosine theta equals 1. This will change the set of values for theta for which the identity is valid. So let's start out with the left side of the equation is sine squared plus cosine squared. The right side is 1. Our domain is any real number. It's a Pythagorean identity. Moving down from that, I'm going to subtract cosine squared theta from both sides. Okay, subtraction, property of equality. POE is always a abbreviation I've used. So we subtracted cosine squared from both sides. Then here I can factor this, right? It's the difference of perfect squares. And factoring is a form of the distributive property. And I just carry this down because I didn't do anything to it. Then I go ahead and divide both sides by 1 minus cosine squared. So I have sine squared theta on the left. I'm dividing both sides by 1 minus cosine theta. This is division, property of equality. And by here, this is where we have a few little issues. I cannot have cosine theta equal to 1 because then I would have 0 on my denominator. So theta cannot equal factors of 2 pi. So we say 2 pi k. Then on the left, we're good. On the right, I'm canceling those out. And I would have 1 plus cosine theta. this still holds true because I have cosine on the bottom. And that one is our substitution property of equality. Okay? I mean, we've not learned to use this property for simplifying, but we're just using 1 over cosine theta over 1 over cosine theta. We're substituting that as equal to 1, which is a funny way to simplify something. But hey, that's all right. It works. Because I assumed my handwriting would be so bad on the last slide, I went ahead and copied my teacher's edition over here just so you could see it a little bit clearer. Okay, it's just showing all the steps. We start with the left side of the equation and mess around with it until we can get the identity. Okay, next, we can start with the more complicated side of the identity. We want to prove and use algebra and prior trig definitions and identities to transform it to the other side. In this case, the more complicated expression is given. So with the last example, we just used the Pythagorean identity, and we messed around with it, divided both sides of the Pythagorean identity with the same expression to come up with identity. And this example, we're using the more complicated one, and we're going to use that and mess around with it to transform it to the other side. Okay? All right. This is the way that I originally did it too. So the left side is given, and we can say that this right here is equivalent to this. It's not the original identity that we're trying to prove, it's just a statement. So this is what I'm starting with. I can say that the numerator is equivalent to 1 minus cosine squared theta because that's the Pythagorean identity. So that's what we're doing here. I just substituted sine squared theta with 1 minus cosine squared theta. And my reason is substitution property. I still have the same domain issues because I have 1 minus cosine theta in the denominator. I am now going to factor this, the distributive property, and that will allow me to simplify, or in the book they call it substitution, just like the last slide, substitution by saying 1 minus cosine theta over 1 minus cosine theta equals 1. The domain has not changed because I still have 1 minus cosine theta in the denominator. But I'm left with this as an answer, which is our identity. Okay, let's try a few of these more independently. I'm going to work through them and talk through them, and hopefully you'll be able to follow along and see what you need to do for your problem set. So here I have tan x equals secant x over cosecant x, and there is my domain. So I'm going to grab the more complicated side and try to mess with it to get back to tan x. So I'm going to grab this and start messing with it to see if I can get back to that. What do we know about secant x and cosecant x? Well, secant x is the same as 1 over cosine x. And cosecant x is 1 over sine x. Well, now I just have two fractions in division. I can simplify those two fractions. I mean, if I said 1 over x divided by 1 over y is equivalent to 1 over x times their reciprocal, y over 1 equals y over x. I'm doing the same thing here. So I have 1 over cosine x times sine x over 1. When I multiply fractions, I multiply straight across. That gives me sine x over cosine x, which is tangent x. I got back to there, which is pretty cool. So we know the identity is true, and we already have the domain written. So prove the following are trigonometric identities, beginning with the side of the equation that seems more complicated and starting the proof by restricting x to values where the identity is valid. Cool, we're good. Well, so at the end of the proof, I'm supposed to say tan x equals secant x over cosecant x for x not equal to pi over 2 plus pi k, because that would give us a 0 here, not there. Goodness, I just made a mess. Awesome, let's try one more. Okay, here's the same one. Now you have to decide which one is more complicated. The left side has 2 terms, the right side only has really 1 term, but they're multiplied. So let's try the more complicated one, which may be the left side, since there's 2 terms. In general, functions composed of multiple terms or a product of multiple terms can seem more complicated than functions having a single term. But it doesn't matter which side you start with. So let's start. I have cotan x plus tan x. So cotangent is 1 over tangent. We know cotangent is 1 over tangent, which is 1 over sine over cosine, which equals cosine over sine. Just making little notes here. So I can say cosine x over sine x plus sine x over cosine x, because tan x is sine x over cosine x. I'm going to, I need to get my denominators with the same terms. This is something we did a lot when we rationalized equations. So in the numerator, I'm going to have cosine x times cosine x plus sine x all over sine x cosine x. Now we're going to rewrite the numerator because that's a lot of duplicate writing. Cosine squared x plus sine squared x all over sine x cosine x, my handwriting. Now we know that this numerator is part of the Pythagorean identity. So I can substitute 1, get my pen back, 1 over sine x cosine x. Which equals 1 over sine x times 1 over cosine x, which equals cosecant x secant x. Which is the right side of our equation. Do you see, this is going to take practice where you just need to try to figure out, look at an equation, like, okay, I don't know, what can I do with that? Okay, I don't know, what can I do with that? What algebra skills, what algebra 2 skills have I learned that will allow me to mess with that? Just things that, and it will take practice. So I should write my answer. Equals, I'll even reorder it, secant x times cosecant x for all real numbers where x can't equal pi over 2 times n for integer n. So that's all I have. Your problem set has quite a few practice problems. And it'll take just a little bit of practice to get used to it, but hopefully you'll find these a little bit fun as you go. Good work today.